All right, in this video, we're going to look at rotations of points. Now, a rotation is just as it sounds, right? We're just going to turn the points or the figure, that makes some sort of the set of points. But there's two things that we need to keep in mind. We need to know which direction we're going to do the rotation and where's the center with which we will turn the figure. So those are going to be things that we need to kind of sort out at the beginning before we actually start rotating our points. And we're going to do this two different ways, each of these problems. We're going to do this a more visual way. We'll actually turn the graph and see the rotation actually taking place. And we'll ignore the picture and come over here and do this a more computational way where we can take the ordered pairs and understand kind of where they'll end up, no matter what, the picture is going to look like. Okay. So I went ahead and plotted the points where they belong, right, to save us some time here. So let's start off with the measurements. Now, the more common angle measurements that you might be asked to rotate are going to be increments of 90 for obvious reasons on the coordinate plane, right? I mean, each of the axes are going to be 90-degree increments. So we technically could rotate this thing any degree measurement we would like, but that greatly complicates our ability to kind of place them accurately without kind of having some sort of tool to measure these angles, okay? So before we move on here, what we need to understand is the angle measurements themselves and the direction that we want to turn these things. So in this example, they actually tell us the angle with which we want to rotate and the direction very specifically, right? So counterclockwise, thinking about a clock, right? If we have a clock that goes in a circle, we know that, the hands on the clock go this way, right? As I'll say, we'll turn it to the left, right? If I started here and I just, like a steering wheel, to the right would be clockwise, and then counterclockwise would be turning it to the left. So if they tell us clockwise or counterclockwise, we're just going to rotate it the direction that we know an actual clock would do, and then the angle measurement would be how much of this will turn. Okay, so we're going to rotate this thing around the origin. So keeping track of our center will be something that we're going to want to do as we move along. So counterclockwise, right, going against the clock would be kind of turning it to the left here. 90 degrees means that this, if I wanted to think about this axis up here, it's going to turn and it's going to face down here as like my x-axis. So I'm just going to do one turn to the left, right, which would be 90 degrees. And what we're looking at is our answer. So to actually rotate these things and figure out where these points will be, we're going to think of this as like our new y-axis and our new x-axis, and I'm going to figure out the position of these points so that when I turn it back to the standard way that my paper is laying, then I'll just plot the points that I had just seen. Okay, so in this case, I know that A, and I'll just write it down here, A is now at what? -7, 2. Right? B is at what? -5, 6. And C is at -1, 4. Right? So I'm looking at my answer. So now that I've turned it, I've jotted down where the points should be. So when I turn this back into this standard position graph, I'm going to graph these points where they belong, right? So I'm going to say, we said that A was at -7, 2. So from here, -7, 2 is my new A value. So that's going to be A prime. B is at -5, 6. -5, 6. That's my B prime. And C was at -1, 4. -1, 4 is C prime. I'll just connect the dots here. As straight as I can get them. Oh, that wasn't very good. There we go. right? But we have it, right? So if I turn this thing 90 degrees counterclockwise, which is the rotation to the left, it should land on top of the one that I drew, right? And then we actually have them named here, so we could do it that way. Now, if I wanted to do this a more, just looking at the ordered pairs and imagining where they would be, then I would need to be familiar with how each of these ordered pairs gets mapped to a new location. So there's formulas for these in terms of rotations. Okay. So the top ones are the common ones. A lot of times people will memorize these. And, of course, whether we're rotating counterclockwise or clockwise, of course, about the origin, then these points will work for two different ways. Because if we rotate 90 degrees to the left, that's going to be the same as 270 degrees to the right. So if we turn our paper, it will actually land in the same spot, each one of these. So this one rule works for either of these rotations, right? So, you can just memorize these adjustments to X and Y, right? And then later on, we will start to rotate around a point that's not the origin. So I'll come back and I'll kind of talk about these rules. Okay. Of course, a rotation 360 turns the paper all the way back around and lands it right back where it was. So the point won't actually change. So not much going on with the 360. Okay. So as we move along, I'll kind of just make note of these so I don't have to keep jumping back and forth with this paper. And, we'll use these. Okay. So if I didn't want to do this graphically, I can say, all right, a counterclockwise 90 degrees is going to have each of my ordered pairs get mapped to a new location that will look like this, right? So basically all I'm going to do here is I'm going to say each of my X, Y ordered pairs are going to swap positions, right? So if I started off with an X and a Y, I should end with this. So the X swaps to a Y position, the Y swaps to an X position, but whatever Y is, it's going to be the opposite sign. So this X value, 2, will come over here to be my new Y value. The Y value, 7, will come over here to be my new X, but I'm going to take the opposite of that, so that'll be negative 7. So same thing here. This 6 as the X will now be my Y. The 5 will be my X, but it'll change signs. The 4 is my Y. The 1 is my X, but the Y is going to change signs here. And then I could check these, right? I mean, if just visually, negative 1, 4, that's my C. Negative 5, 6. Negative 7, 2. So yeah, this change in my X, Y ordered pairs lands it right on top of the figure that I had rotated. Right? All right, let's try it. So we got these 4 points. Went ahead and plotted them. I'm rotating around the origin again. Right? I'm just going to kind of make a note of that, just to keep things consistent as we move through. Okay. So this time I want to rotate 90 degrees clockwise. So clockwise is going to be one rotation to the right, moving like a clock would. Okay. So I'm just going to turn it 1 turn to the right. Right? And again, what we're looking at is our answer. So all I want to do is envision that this is my new y-axis and x-axis, and I want to write down where these points are so that I know where the rotated figure belongs. Right? So what do we start off with? T. So T is, where's T at? Looks like 1, 2, 3, 4, 5, 5. Right. U is what? 7, 1. T, V. V is what? 3, 3. And W is what? 1, 7. Right? So now that I got the positions down, I'm going to turn it back where it belongs. and I'm going to plot these points. So I'll have my pre-image getting mapped to my rotated image over here. Right, so what do we got? T was 5, 5. U was 7, 1. V was 3, 3. And W was 1, 7. So what was this? This was T prime, U prime, V prime, W prime. And then I'll just connect the dots here. And again, these rotations should look like the shape that was turned, right? So again, a rotation is what we would call a rigid transformation because it preserves the size and shape of the figure that we're moving, right? So even though it's in a different spot, the size of this rhombus and the exact shape of it are the same, right? So it's a rigid transformation. Okay. Now the computational way works out nicely. Okay, we can say, let's see, rotating it clockwise about the origin would swap the position of x and y, but the x will now be negative, right? So all I really need to do here is take each of these ordered pairs and adjust them accordingly. So my x, which is -5, is now going to be my y, right, because it's in the y position, but it's going to change sign. So this guy is now going to be a positive. The y, 5, is going to move to the x position, and he's going to stay exactly the same. So the x, which is negative, is now going to be positive. The y, 7, switches, and it stays as it is. This x is negative. He's going to change. This y stays the same. This x changes when he swaps. This y stays the same. So the good thing is we have these rotated images, points for our image. We could see that they're the same. Or if I just kind of noted them in my head and plotted them, we can see that these things match up: 7, 1, 3, 3, 1, 7. Right. So this computational way works nicely when our ordered pairs are really big, or they're fractions or decimals or something that isn't quite as friendly to graph. So sometimes a lot of people will just start to memorize these like formulas. That way they don't have to kind of be encumbered by, plotting the points and actually moving it. You can kind of just envision where the new points are supposed to be without doing a lot of hassle. But they are, things that you would have to memorize. So a lot of people shy away from that kind of thing. So it's kind of up to you there. Let's try another one. Okay, so we're rotating about the origin again. I'm just going to make note of that. Right? Now we're going to do negative. So it doesn't say clockwise or counterclockwise. It actually just gives us the angle as either a positive angle or a negative angle. So to help justify which direction is positive and negative, any angle that we have on a coordinate plane, the initial position is going to be along this positive x-axis, right? So if I start here, I can think, well, if I go up, that's going to be positive, and if I go down, that's going to be negative. So if I took this side of my graph, if I want a negative 270, I'm going to turn this down, which would be a negative angle, or I can turn it up, which would be a positive angle, right? So 270 is an increment of 90, right? This is going to be 93 times. So all I'm going to do is I'm going to turn it downwards, right, for a negative angle, 3 turns, right, to the right to make 270. So this is 90 degrees, right? This is 180 degrees. This is 270 degrees. And now, again, I'm looking at my answer, right, the image of this thing that has been rotated. So I'm going to, again, just jot these points down. So J, is located where? -7, -6. Okay. What we got? -5, -3, it looks like. L is 0, -2. And M is, what we got? -4, -8. Right? And then we can turn this back and then plot these points. Right? So -7, -6, -5, -3, 0, -2, -4, -8. Connect these dots so I can see my figure. I didn't name them, so J, which one? J prime is here. K was -5, -3. L prime, M prime. So there we go. We can see that our image, right now, we turned it, -270. Now, I mean, if you wanted to, a lot of times people will say, well, -270 is the same as a +90. So, if you wanted to just do one turn to the left, that would be the same as moving your paper 3 turns to the right. So, if you want to shorthand your rotations to put it in the position that it belongs, there's nothing wrong with that. Right? Now, if we wanted to not do it with the picture, right, a -270-degree turn would map our ordered pairs to this position. So we can go through and say the X is going to change position, but it's going to stay the same sign. So this is going to be a -6. The Y is going to switch positions, and it's going to switch signs. So this will be a negative, right? So the X comes over here. The Y becomes a negative. The X comes over here. The Y, which is 0, becomes negative, which doesn't really make any sense because it's 0, so we'll just leave it. The X comes over here. The Y becomes negative. And then we can see, right? -7, -6, -5, 3, 0, 2. They all match up, right? We don't have to really envision where these points are, right? Okay, let's give another one a try. So let's move on to, let's say we're not rotating around the origin, right? So we still have our points. We're still going to plot them just like normal, right? These positions on the graph do not change. What is going to change, though, is how we envision where these points are. Because since our new origin, so to speak, right, our point that we're rotating around, 0, 1, we're starting off with one that's pretty close to the origin. 0, 1 is right here. Again, I'm going to make note of that. Now, when we did these points here that were rotated around the origin, these ordered pairs were literally the distance from the origin to this point. So we could look at these as distances that were turning to a new spot, right? But if we're not rotating around the origin anymore, then the distance from this center of rotation to these points are not actually 4, 5, 6, 2, 1, 2, right? They're something different. So we're still going to turn the figure in the same manner, right? We're going to turn it so that it lands where it belongs, the negative rotation. So negative is down, right? So I'm going to say 2 rotations in the negative direction. And again, I'm looking at where my answer is, but in order to plot it where it belongs, I need to see where it rotated from this center of rotation. So in this case, we're going to not say that this is like -1, 2, because -1, 2 is a distance from the origin. That's not what we want. So I'm going to use a vector form to show the movement from the center up to the point that we want, so that movement, I can shift these points that same direction from this origin to get to where they ought to be on the graph. So we talked about component form of a vector in the translation video that I made. So if you're not really sure what I'm doing here, then you can kind of take a look at that. So I'm looking at f, right? In order to get to f prime, right, I'm going to need to move left 1 and up 3. So left 1 and up 3. I'm just going to jot this down. Whoops, there we go. Okay. In order to get to D prime, I need to, remember from here, 1, 2, 3, 4 to the left. 4 to the left. 1, 2, 3, 4 down from this center, right? And then E prime, I'm moving 1, 2, 3, 4, 5, 6 to the left. 1, 2, 3, up 3. So 6 to the left, up 3. So this vector, this component form vector, shows the movement from that center of rotation over to where I want the point to be, right? So now that I have these movements, I'm going to turn it back to where it belongs, and then I'm going to move these directions to get to the point that gets mapped from the image, right? So kind of looking at them upside down here, F was left 1, up 3, right? So from here, left 1, up 3 puts us at a new F prime value, right? D went left 4, down 4. So left 4, 1, 2, 3, 4, 1, 2, 3, 4. This is D prime. E prime went left 6, up 3. So from here, 1, 2, 3, 4, 5, 6, 1, 2, 3. That was E. And then again, I can draw my figure. All right, connect the dots here. Because remember, in a rotation, all of the points should stay the same distance from this thing. So the distance from here to F should be the same as the distance from here to F prime, right? Otherwise, if that's not what's happening here, then we did the rotation incorrectly, right? Because you're thinking of a circle, right? All of these points are kind of on the edge of a circle. The radius of a circle stays the same. So this rotation should preserve this distance. That's why we're looking at these component form vectors to show the distance. We want that distance to stay the same. Now, if we're not shifting around the origin, this is going to change the way we do these points here, because basically what these rules are saying is that these rules here work about the origin. So we could shift our center of rotation back to the origin so that we can use these rules. Once we shift and then use these rules to rotate, then we want to shift it back to the center of rotation. So these incorporate these adjustments to bring the points back to the center, rotate them, and then put them back out where they belong. So we don't really need to think about all these adjustments. We can just use these rules if we would like. So I'm going to go through them. I'm just going to jot them down and just use them, right? So in this case, I'm using the point where this is my H and this is my K, right? So in this case, it's going to be the opposite of X, right? Plus 2 H's, that's an H. And then the opposite of Y, plus 2 K's. Okay. So I'm going to take my X and Y ordered pairs, plug them into here using these H's and K's. Okay. So we want the opposite of X, so the opposite of 4 is negative 4, plus 2 times the H value, and the H value here is 0, right? And then the opposite of Y, plus 2 times the K value. So 2 times 0 is 0, plus negative 4 is negative 4, right? 2 times 1 is 2. 2 plus a negative 5 is negative 3. And if we wanted to check, right, this is D prime. D prime is at -4, -3. 1, 2, 3, 4, 1, 2. Looking good. Right? Let's do E. Right? Taking the opposite of X, so it's the opposite plus 2 times H. Right? The opposite of -2 plus 2 times K. Right? So 2 times 0 plus -6. Right? 2 times 1 is 2, plus 2 is 4. And then doing this last point, change the sign. 2 times the H value. Right? Change the sign. 2 times the Y value. So 0 plus -1, 2 plus 2. -1, 4, looks good. -6, 4, looks good. Didn't even really need these. I can just use this mapping to get to my new point, if that's what I would like to do. All right, let's try another one of these around a point that's not the origin, just to get another feel for it here. Okay, so we got our points. I went ahead and plotted them. Awesome, right? I'm rotating 90 degrees. That's a positive 90 degrees, right? Because it doesn't say counterclockwise or clockwise, so positive 90, we know which direction, around the point 4, 2. So the first thing I'm going to do is I'm going to make note of where 4, 2 is. 1, 2, 3, 4. That's my center. So if I'm going to do this visually, right, I need to turn it. Let's see. Positive 90 is to the left, 1 turn. Right? Now from this center of rotation, I need the distance that I travel to get to these points. So I'm going to label these again as vectors. This is going to go left 1, down 2. Right? In order to get to B, I'm going to go what? Right 1, 1, 2, 3, 4, 5, down 5. Right? Then I'm going to go 1, 2, 3, 4, up 1 to get to C. Right? Now that I know my movements, turn this back where it belongs. Move these points from our new origin, not this guy, right? From this guy. These are movements from our center. So A goes what? Left 1, down 2. So left 1, down 2. So A prime goes here, right? This one goes right 1, down 5. 1, 2, 3, 4, 5. C goes right 4, up 1. Now I can connect these dots. Right? Each of these points should be the same distance from the center. The distance that B is should be the same distance over here. Right? If I drew a line from C and then went to C prime, this thing should make a 90-degree angle. Right, if you want to envision it this way, because sometimes it's kind of hard to see if you did it correctly. So if I draw a line from the center to C and then another straight line out to C prime, if it doesn't meet at a 90-degree angle, then I didn't really rotate it 90 degrees, right? I guess that makes sense if you want to kind of envision that. All right, so using my point of center here for the rotation, a 90-degree rotation around this point will map these values like this. Just using my formula. I'm just going to write the formula down, and then I'm going to use the formula. Right? So, I'm going to take each of these points, plug them into the formula. Remember, this is H, this is K. So here I want my Y value, which is 3. I want the opposite. So this is going to be -3 plus the K value, which is 2, plus the H value, which is 4. And then I want X, which is just a +2. I'll just write this down here. minus the h, this time, is a minus 4, plus the k value, so plus 2. So that gives us what? Negative 3 plus 2 is negative 1, plus 4 is 3, right? 2 minus 4 is negative 2, plus 2 is 0. Okay, b, I'm going to take the opposite of my y, which is now going to be a negative 1. I'm going to add the k, which is 2, add the h, which is 4. Then I'm going to take x as it lies, right, which is negative. Not going to change the sign. Minus the h, which was 4, plus the k, which is 2. So what do we got? Negative 1 plus 2 is 1, plus 4 is 5. Negative 5 plus 2 is negative 3. And then finally c, I want the x value, the y value to be the opposite. So I'm going to change him to be a positive, plus k, plus h again. Then we're going to keep x as it is, minus h plus k again. So what do we got? 2 and 2 is 4, plus 4 is 8. 1 and 2 is 3. And then if I plot these, 8, 3, 5, negative 3, 3, 0, looking good, right? So again, just to recap, this method, it's a lot of memorization, so a lot of people will shy away from that, okay? But in reality, it really ends up being a go-to if our points, like I said, get really big, or if you have fractions or decimals. So that's where this really gets a chance to shine here. Hope that helped.